let's say we were given a problem where we were given some kind of image. We were asked, can you approximate the center of gravity for that person given their height, weight, the amount of weight they're holding, and then basically find all the angles of the body parts, right? So maybe our first step in the analysis would be to take that image and then make a series of points that describe the person's shape, right? Let's do this. These markers give us some locations of points that are, features on the body that we can use to describe pretty much everything about that person, right? Say all of their arms are straight, the torso is straight, legs are straight. We can now label all of these points. Let's do that. Say this is A, B, C, D, E, F, G, H, and I. Right? Those are points that we just kind of clicked on this image. And we want to say that C to some reference location, H, or the ground here, we can say this is total height. This is total person's body height, right? So we can also say that we measured the person's width of the torso. Say height and width. And we're going to first start off, we're just going to say, hey, I think the CG is probably somewhere in the middle of this person. Let's call this like CG prime. It's like our guess. It's our guess for where the CG probably is. And we're going to use our analysis here just to find out, how off are we? Is the CG actually here? Right? Is the CG actually here? These kind of things. So what we can do is find a vector pointing from our approximate CG to the real one, right? We could point a vector there. And that gives us the real CG for the person in terms of some kind of vector offset from our CG prime. So we also have to kind of make some assumptions here, right? We got to assume that all parts of the body have equal density, right? So, the torso is as dense as the entire arm, as dense as the entire head, right? And we can also do an assumption that says, let's just make the body parts simple rectangles. Right? So what we can do is just bound all parts of the body with simple rectangles. Let's do that here. Make a little robot guy. Relabel our points. Say this is B. These arms connect at the kind of the extremes of this rectangle, this torso. And again, all these things are going to be assumptions. Okay, so now let's talk about where the CG of all these rectangles has to be, right? So the separate CGs of each body part should be in the middle of these rectangles, right? So this is CG of AB, section AB. Gotta make another one. Let's call that J. So this is all right. So we're describing these points, and I wrote this extra point O, which we can say is like our coordinate system 0, 0. So point O is our origin, right? We could say, hey, let's try to find that CG in terms of this person's torso center mass, right? So taking this system, we can say that the sum of vector lengths from the origin to each CG crossed with the force divided by the sum of those forces is equal to the center of gravity. All right, so what does this look like? That looks like a sum of moments about some origin divided by the sum of forces. So that's no big deal. We can do that real quick. So let's real quick, let's think about something. We can make this really simple because we know that the vector gravity acts downwards all the time. So let's just say, all right, so we know that this equation right here is going to be some kind of like lengths times forces over the forces. And one thing common to all these forces is this idea that that gravity, the vector gravity, is common to both the top and the bottom. So if you look at that, that's going to be like Li cross gravity, right, times some mass I, right? And mass is a scalar. Gravity is your vector. But the thing is, right, we have the sum of a gravity vector times each mass. So our gravity vector really gets pulled out of this summation. We get sum of masses times our gravity vector. So you can see that now we can just cancel these gravity vectors, right? And now we get the summation of our lengths. This is a vector. We just say that's now times a scalar, the mass divided by the summation of masses, right? So we don't need to use these cross products anymore. That's pretty convenient. So let's bring this over here. Let's say this right, it simplifies to this because gravity is common. So gravity vector is common between the forces. Okay. So now all we need to do is take this and we say, okay, can we describe the length vectors and the masses? Okay, so how do we find our length vectors? Let's just describe them. All of the ones we need. We need LB to A. We need LD to E. LJ to C. LF to H. G to I. What else do we need? We need the length vectors from the origin to each body insertion point. So that's going to be LO to A, O to B, LO. No, we need LO to B. Sorry. LOJ, LOD, LO to A or F. Right. So let's actually flip these around. It's going to be convenient. So if we can describe the vectors B to A, B to A, D to E, right, J to C, all these vectors, so if we can somehow describe them, then, and also O to B, O to J, O to D, O to F, and O to G. Right? Let's say we have those vectors as like just variables. I say we describe them that way. Well, if we want to find a vector pointing from O to each center of gravity, say like here, right? How do we do that? Well, I know that if we have a vector B to A, and we have a length right in the middle of that vector that describes our CG point, right? Then, so this component is BAX and BAY over 2, right? So that means that all the vectors, B to A, J to C, D to E, take 1/2 of the vector and you got your CG locations for that component. All right, so let's make a new vector system here. Let's call this LO to the CG of arm1, right? And for convenience, let's just write some more points out there. Let's just write, say, where are we at? J, we'll call this point K, L, M, N, P. So we want L, O to K. So that's going to be equal to LOB plus 1/2 LB to A, right? LO to L equals LO to D plus LD to E, or 1/2 LD to E. And that's similar to all these other ones. So let's do that real quick. Okay, so now we have a vectors for the center of the torso, coming from the center of the torso to each one of our center of gravities. All right, so let's rewrite that again. Now we can just call these points cycle. Say A, B, C, D, E, F, G, H, I, J. All right, that's convenient, right? If we do this, like everything up to now has been like a setup of our vectors pointing to our center of gravities, right? So now we have to kind of find the lengths or the components of all of our vectors that we just made. Like, what is BAX, BA? What are all these things, right? And we can do that in terms of a person's height, right? Just by knowing what's the length of arms based on someone's height. And then we can do the same thing for head, legs, torso, right? So let's do that real quick. So let's just go to Google. We could type in human body ratios as our search. Maybe go to our images, find one that we like. This one looks good. Has all of our height in terms of these have heights in terms, or lengths in terms of body height, so that's perfect. So let's just write these equations down real quick. Let's say that an arm length look like it equals 0.186 plus 0.146 plus 0.108 times height. Legs, that's 0.53 times height. Torso, let's call that 0.818 minus, where's this one, 0.53. Also the torso width too, 0.191. Is that all of them? We need the head too. Let's say that's 0.13 times the height. Okay, so now we can get rid of this figure. Okay, and now let's use all this stuff to look at our variables. Let's say we have length BA. BA length is equal to this thing, right? All that stuff. Let's call that length K. And what else is described by length K? You got DE. DE is another arm. That's length K. We have torso or leg lengths, so we can say FH is this one, 0.53. Let's Let's call it L. GI. L. JC equals head height, M. And then we need to describe these points on the torso, B, D, F, G. So then we need to talk about, like, what's the width B to D? B to D. Torso width, call that N. And then B to F, let's call just BF is torso height. Torso length, this one. That one. Let's call that little P. Alright, so we can use all this stuff to find our vectors, LBA, LOB, right? All this stuff. And we can draw this guy again. So that's K. K. M. N. P. L. L. So now remember that we know these angles from the horizontal to the arm and stuff. That was all described up here. We know them. They're just a bunch of thetas, right? Say arm has some theta 1. You got head. This is left arm. Head makes some angle theta 2. Right arm makes an angle 3. And the left and right legs make some other angle, theta 4 and theta 5. Now we can use that information to go ahead and make a system of points that go and describe the locations of all these vector coordinates that we have, right? Okay, so we can use this information to go ahead and find the locations of all our points, A through J, right? And say, use this to describe points A through J. So what do we got for A? Point A, that's A, B, J, C, D, E, and F, G, H, I. And that's O. All right, so yeah, we got to look at those points in relation to O, point, which gives us our 0, 0, right? So we need to find what is the location of point A. Point A is going to be something, it's going to be point B plus the length of the arm, K, cosine theta 1, and then it's going to be point, so this is point BX, BY, plus K sine theta 1. B, what is B? It's like in X we got the negative half of our torso, so negative 1 over n, or I'm sorry, negative 1/2 n, and then we have 1/2 in the positive, and that's m, right? No, that's not n, that's p, bf, right? So the length of the torso, bf, is p, so that's 1/2 p y in the y. C, that is point j, so jx plus m cosine theta 2, jy plus m sine theta 2. Let's fill out the rest real quick. Okay, now that we have all the coordinates for our points, right, we can use them to describe our vectors. So for example, the component BAX, right here, BAX, will be BAX, right? We gotta find that component. BAX, BAY. Well, we know that the arm length is K. We know the angle here is theta 1. So then BAX must be equal to K cosine theta 1, right? And then BAY is K sine theta 1. All right, so let's look at this whole thing again in terms of AB here. So that we know the vector AB, now this must be equal to the point A, right, minus point B, because that gives us K cosine K sine. So A minus B is equal to BAX, BAY. All right, so we can use all these relations to back out all of our points that we want, right? So let's do that real quick. All right, so now, remember, now we can use this information to basically plug it all into our vector relationships and find these quantities A through J. And we're just going to use those things, right? We're going to say, I'm going to redraw our little robot guy again. And let's label all the points that we care about. Now let's look at the vectors we want. And let's just simply write these things down right here. LOA, LOK, LOL. Copy this, make sure we're not losing information here. Okay, we got A, B. Let's do that. M, L, C, D, E, F. And LOA is just going to be point A that we found up here, right? That's point A. But let's move that down to the bottom of the list. And then what else free variable do we have? We used a bunch. We're up to like QR now. It's like QR. All right, so now what do we need? We need the weights. We need masses of each component. And to find that, we can go to the internet again. So we can say, let's find the weight of some body part. And link gives me this nice table. We can just use to copy and yeah. So let's just copy this table. Use it here. All right. So now we can say the mass of the arm. What do we got here? Let's say this is use average values. Arm is 5%. So it's 5% of the total weight of the person. Mass of head is 8%. Whole trunk, 54%. The leg, total leg is 18%. So that's cool. Now we also need that weight. What do we call the weight? F. Right. So now we can talk about taking these vectors and multiplying them by our masses. So let's go take this. Let's take this and say, let's make more variables. So we make a table here for our length vectors and our weights. And then we say lengths times weights, right? Let's do that. So LOK, what do we got for LOK? LOK goes from the origin to the center of mass of the arm. So LOK needs to be multiplied by the mass of the arm, S, to give our vector AS, BS, LOM. Where does LOM go? That's the other arm, so it needs S again. That's CS, DS. LOL goes to the head. Head is T. Right, LOL goes to that. Yep, LOL go. All right, so now it's ET, FT, N. What do we got for N? It goes to the leg. The leg is going to be V. GV, HV. That's another leg here. IV, JV. And then here's this, this is going to be the force, right? Mass of the object that the person's holding. That's LOA. So let's come down. LOA is going to be, we got big F. And this is going to be QF, Q, or RF. Those are big Fs. Not to be confused with the little f, right? What else do we have? We have the trunk. So our length vector here is LO to O, and that's 0, 0. Right, so what do we have for this one? That's also 0, 0. But this one's going to be the weight of the trunk, which is U. That's probably the easiest one to forget because it's not associated with a vector that we described, but make sure you also include the O to O vectors. And then we do a summation. Summation of the weight is 2s plus 2t plus f plus u. And that's sum of masses. So there we go. We got that one. Then we got to sum all these deals, all these vectors, into a final vector that is the sum of Li, Wi. Let's call that vector. What's our last two letters? We got U, V, W is already taken. We got X, Y. Well, that's convenient. All right. So now the center of gravity is a vector XY divided by 2s plus 2t plus f plus u. And that's big F. Put like a little thing on the end of this thing just to make sure you know it's not that little f. All right, so that's, remember the equation we're trying to use is this Li Wi divided by the sum, oh man, that's not Wi, that's Mi, the sum of Mi. And this, what does this give you? This is the offset vector from that CG guess that we made, CG prime equals some point 0, 0. Right? So that's the offset from here. Oh. So in this case, it's probably some kind of vector here that shifts the center of gravity just a little bit left, or person's right, because of this weight A. Right now, the rest of this thing is symmetric, really, about O. All right. Okay, so say we're pretty much given. We're given all of these like points. I mean, this problem gets super easy, doesn't it? Okay, well, I hope this helps on your homework. Good luck.